The first ray of sunshine in the morning falls on the calm sea surface. A research vessel is slowly sailing in a bay in Chile, South America. Underneath the sea, divers discovered a shocking sight. The seabed, which should have been covered with local shellfish and seaweed, is now densely packed with giant geoduck. These unwelcome guests from the North Pacific are quietly establishing their own kingdoms in this sea far from their hometowns. This is not an isolated case. From the North Sea coast of Europe to Tasmania in the southern hemisphere, from the bays of Japan to the fjords of New Zealand. Similar scenes are constantly unfolding around the world. Geoduck, a precious seafood once only found on the west coast of North America. Nowadays, it is expanding at an astonishing speed into global waters. They are no longer silent challengers that divers need to risk their lives to capture. But it has evolved into a silent invader that changes the global marine ecology. To understand why geoduck can successfully invade on a global scale, we must delve into the amazing survival strategies of this organism. In the long process of evolution, geoduck have developed a series of biological characteristics that make them perfect invaders. Let's first focus on their amazing lifespan. Geoduck are one of the longest-lived invertebrates known on Earth, with a lifespan that can easily exceed 100 years. According to scientific research records, the oldest discovered individual of the elephant clam has reached the age of 168 years. This extraordinary lifespan means that once a population is established in a new environment, they will continue to affect the local ecosystem for centuries. Even more shocking is that the growth and development of geoduck seem to never stop. As long as the environment is suitable, they will continue to grow. In the waters of British Columbia, Canada, researchers have discovered giant individuals with shells up to 1.2 meters long, weighing over 300 kilograms. The unique physiological structure of the elephant clam is the key to its successful invasion. They're iconic, giant siphon tubes that cannot be fully retracted into their shells. Actually, it is a highly specialized life support system. This siphon tube is divided into two independent channels by a diaphragm inside. One is used to inhale seawater rich in oxygen and food, and the other is used to excrete metabolic waste. This exquisite design allows the elephant clam to bury itself at a depth of 1 meter below the seabed. Only expose the end of the siphon tube to the sand surface, ensuring maximum safety while efficiently completing life activities. Research shows that an adult elephant clam can filter over 500 liters of seawater per day. This number means that a medium-sized population of geoduck can grow within a day. It can handle seawater equivalent to several standard swimming pool volumes. This powerful filtering ability not only provides them with sufficient food sources. This enables them to gain an absolute advantage in competition with other filter-feeding animals. Breeding strategy is another weapon for geoduck to conquer new environments. These organisms possess astonishing reproductive abilities. A sexually mature elephant clam can release over 1 billion gametes during a breeding season. When environmental conditions such as water temperature and salinity reach specific thresholds, the geoduck in the entire region will be released synchronously, forming a massive, spawning event. This synchronization strategy greatly improves the success rate of fertilization, ensuring that there are sufficient numbers of larvae joining the army of planktonic organisms. The larval stage of geoduck lasts for about 4 to 6 weeks, during which time these tiny lives drift with the flow and can spread hundreds of kilometers away at the farthest. During the planktonic stage, larvae undergo multiple developmental stages and only settle down when they find suitable substrate. Start the process of its transformation into an adult. This ability to actively choose a settlement location further increases their success rate in establishing themselves in new environments. Environmental tolerance is an important reason why toads can survive in diverse environments. They can adapt to a temperature range from 2 degrees Celsius near freezing to relatively warm 20 degrees Celsius. The salinity tolerance range also ranges from nearly 15 per thousand of freshwater to 35 per thousand of completely seawater. What's even more impressive is that they have extraordinary endurance against low oxygen environments. When eutrophication of water leads to hypoxia in the bottom layer, most marine organisms find it difficult to survive. However, geoduck can survive for several weeks by using strategies such as reducing metabolic rate and adjusting filter feeding frequency. The global spread history of geoduck is actually a microcosm of human activities changing the global ecology. How could these organisms, originally limited to the Pacific coast of North America, spread globally in just a few decades? The answer lies within the workings of modern human civilization. The introduction of aquaculture is the initial diffusion pathway. Starting from the 1960s, due to overfishing, the resources of geoduck originating from North America have decreased. With the continuous growth of global market demand, multiple countries have begun to try introducing and breeding species. Japan first attempted to introduce geoduck into its northern waters in 1968. Subsequently, China, South Korea, Chile and other countries also joined the ranks of introduction. These introduction plans often carry a beautiful vision for economic development, but ignore potential ecological risks. In 1994, a Chilean aquaculture company's oyster farm on Chiloé Island suffered damage to its protective net due to a storm. Thousands of species of clams have escaped into the natural environment. Due to the suitable marine environment and lack of natural enemies, these escaped individuals quickly established wild populations. By 2010, the distribution range of geoduck in southern Chile had exceeded 200 kilometers along the coastline. The highest population density reached 8 individuals per square meter, causing serious impact on the local underwater ecosystem. Ship ballast water propagation is a more covert invasion channel. Modern cargo ships need to carry tens of thousands of tons of ballast water to maintain navigation stability. These seawater loaded at the loading port contain tiny biological components of the local marine ecosystem. This includes planktonic larvae of geoduck. When the ship arrives at the destination port and discharges ballast water, these invisible stowaways are introduced into a new environment. A survey of major ports worldwide shows a single cargo ship's ballast water discharge may contain tens of thousands of individual marine organisms. Although the International Maritime Organization adopted the Convention on Ballast Water Management in 2004. Ships are required to treat ballast water, but the comprehensive implementation of the convention is progressing slowly. What is even more worrying is that even after processing, due to its strong environmental tolerance, the larvae of geoduck may still survive. Live seafood trade and leisure activities constitute another important route of transmission. With the expansion of the global seafood market, accidental escape may occur during the transportation and temporary storage of live geoduck. In addition, fishing enthusiasts in some regions are accustomed to using live shellfish as bait. This inadvertently provided convenience for the spread of geoduck. In Puget Sound, Washington State, USA, researchers have previously discovered individuals of geoduck introduced as fishing bait. Climate change has also invisibly promoted the expansion of geoduck. As global ocean temperatures rise, some sea areas that were originally too cold to be suitable for the survival of barnacles are becoming increasingly cold. Now it has also become suitable for their settlement. The water temperature in some parts of the North Atlantic has risen by 1.5 degrees Celsius in the past 30 years. This creates conditions for the expansion of toads to higher latitudes. When the elephant clam successfully invades a new ecosystem, the chain reaction it triggers is often beyond imagination. This seemingly sluggish creature actually possesses the ability to alter the entire marine ecosystem. The most direct impact is reflected in the transformation of the underwater physical environment. Geoduck are typical ecosystem engineers who rely on their own existence and activities, fundamentally altering the physical structure of habitats. In the Wadden Sea off the coast of the North Sea in Germany, researchers recorded the dramatic changes in the underwater environment after the invasion of geoduck. The soft seabed, originally dominated by fine sand and silt, has transformed into a hard, shell beach after being inhabited by geoduck for 5 years. This change in sediment directly resulted in the local endemic species. The population of clams in the North Sea has decreased by 70%, and some polychaetes and amphipods that rely on soft substrates for survival have almost disappeared. The degradation of seagrass beds is another heartbreaking ecological disaster. Seaweed beds are known as the tropical rainforests of the ocean, although their coverage area is less than 0.2% of the total ocean area. But it provides habitats for countless marine organisms and stores 10% of the world's ocean carbon storage. In Kepela Port, New Zealand, the invasion of geoduck has led to a 45% reduction in the local seagrass bed area over a decade. Researchers have found through long-term observation that the digging activities of geoduck can damage the roots of seagrass. And its powerful filtering behavior will reduce the nutrients available for seagrass growth in the water. The nutritional cascade effect is a deeper-level impact brought about by the invasion of bivalves. As an efficient filter eater, geoduck consume a large amount of phytoplankton and organic particulate matter in the water. Research in Puget Sound, USA shows that when the density of geoduck reaches 5 per square meter, they can filter 30% of the entire water body within 24 hours. This excessive filter feeding not only makes the water exceptionally clear, but also leads to a sharp decline in the number of planktonic organisms. This further affects fish and crustaceans that feed on plankton. The population of local characteristic herring has decreased by 25% as a result. This has also affected seabirds and marine mammals that primarily rely on herring as their food source. The loss of biodiversity may be the most irreparable loss. In invasive areas, geoduck often form a single dominant population, displacing local species. A study in Hokkaido, Japan shows that 15 years after the invasion of geoduck, the number of benthic species in the local intertidal zone decreased from 86 to 34, and the species richness decreased by 60%. What is even more worrying is that some endemic and endangered species are facing the threat of extinction as a result. In Tasmania, Australia, the unique red-handed fish is on the brink of extinction due to the destruction of its habitat by geoduck. Economic losses cannot be ignored either. It is estimated that the economic losses caused by marine life invasion worldwide exceed $10 billion annually. Among them, geoduck account for a considerable proportion. These losses include multiple aspects such as the reduction of fishery resources, damage to aquaculture, and increased maintenance costs of port facilities. In Nova Scotia, Canada, the famous scallop fishery has experienced a 40% reduction in production due to the invasion of geoduck, directly causing over 300 fishing families to fall into difficulties. Faced with the invasion situation of geoduck, scientists and environmentalists around the world are engaged in a difficult and protracted defense war. The front line of this battle extends from the coastline to the deep sea. We need to use the most advanced technological means and invest huge manpower and material resources. Monitoring is the first line of defense in the defense system. Traditional diving surveys are still an important way to obtain accurate data. In the fjords of Norway, A diving team composed of marine biologists conducts over 1,000 diving surveys annually. Detailed records of the distribution range, population density, and growth status of the elephant clam. These divers need to work in cold waters with visibility of less than 5 meters, facing strong currents and complex terrain. Every dive is a severe test of professional skills. They use underwater samples and laser rangefinders to establish accurate three-dimensional distribution maps. Provide key data for subsequent clearance actions. Modern technology has brought revolutionary changes to monitoring work. The application of environmental DNA technology allows researchers to avoid direct observation. We can detect the presence of geoduck through water sample analysis. Faced with the huge investment and arduous challenges required to remove geoduck, an innovative idea is gradually emerging. Can this invasive species be transformed into valuable resources and controlled through market mechanisms? This strategy of replacing control with capture has shown great potential in practice, but it is also accompanied by complex management challenges. Commercial fishing is the most direct way of utilization. In Chile, the local fisheries department has developed a sustainable fishing management system specifically to address the invasion of bivalves. They issue special permits allowing fishermen to fish for geoduck in specific areas. But strict quotas and size restrictions must be followed. This system not only effectively controls the population of geoduck, but also creates new employment opportunities for the local area. In 2022, Chile's export value of geoduck reached $12 million. At the same time, approximately $3 million in clearance costs were saved. Market development is a key link in turning enemies into friends. Due to the possible differences in taste and flavor between the invasive geoduck and their native habitat, targeted market development is needed. Some top European restaurants have innovatively added geoduck to their menus, using its wild and sustainable characteristics as selling points. In Denmark, the clam-like cuisine developed by Michelin 3-star restaurant, Grum, has even become a signature dish, driven consumer demand throughout the Nordic region. The extension of the deep processing industry chain has greatly enhanced the economic value of geoduck. In addition to the traditional fresh food market, researchers have developed a variety of high value-added products. The shell of geoduck is rich in high-quality calcium carbonate, which can be used as biomedical materials after processing. Used for bone transplantation and tooth restoration. In Germany, a biotechnology company specializes in collecting elephant clam shells. Produce high-purity medical-grade hydroxyapatite worth €200 per kilogram. Technological innovation further expands the utilization channels. The strong and tough foot silk protein of geoduck has unique biocompatibility and can be used to develop new types of biological adhesives. A research team from the Massachusetts Institute of Technology in the United States has successfully imitated the structure of mucin from geoduck. Develop surgical adhesive that can maintain strong adhesion in humid environments. The commercialization of this technology has enabled the removal of harmful organisms that originally required payment. It has become a precious raw material worth thousands of dollars per kilogram. However, the strategy of using capture instead of control also faces severe management challenges. The most prominent problem is the paradox of value. Once the elephant pulls out the clam and generates considerable economic value, illegal transplantation and intentional proliferation may occur. In Jeju Island, South Korea, there was an incident where farmers illegally transplanted geoduck into new waters, causing all previous efforts in prevention and control to be in vain. To this end, countries have gradually established comprehensive traceability systems. By using genetic markers and blockchain technology, ensure that every elephant clam on the market can be traced back to its place of origin. Another challenge is food safety regulation. Invasive geoduck may accumulate pollutants in the environment or carry pathogens that are not present locally. The EU has established strict testing standards for this purpose. Require all listed invasive species, such as clams, to undergo testing for 58 indicators including heavy metals, microorganisms, and biotoxins. This set of standards has now become a global model, ensuring the safety of products. The global invasion history of geoduck has prompted the international community to deeply reflect on the shortcomings of the existing ocean governance system, and driving a new round of collaborative cooperation. This crisis reveals not only the problems of individual species, but also a systemic challenge to global marine ecological governance. The improvement of international regulations is the institutional foundation for responding to crises. After years of delay, the International Convention for the Management of Ships' Ballast Water finally came into full effect in 2019. The new convention requires all ships to install ballast water treatment systems. Kill over 95% of organisms in water using filtration, ultraviolet radiation, or chemical methods. This measure is expected to reduce the risk of biological invasion transmitted through ballast water by 80%. However, the implementation of the convention still faces challenges, particularly in terms of technical requirements and regulatory costs for retrofitting old ships. Regional cooperation mechanisms have shown strong vitality in practice. The European Union has established the Marine Invasive Species Information Exchange System, integrated monitoring data from 28 member countries to achieve real-time warning and rapid response. When a member country discovers a new population of geoduck, the system will issue an alert to all potentially affected countries within 24 hours. This mechanism successfully prevented the spread of elephant toads to the eastern Baltic Sea in 2021. Technological innovation is changing the way global collaboration is conducted. The Global Invasive Species Observation Network developed by the Monterey Bay Aquarium Research Institute in the United States, using artificial intelligence technology to analyze data from satellites, drones, and underwater robots, can predict the possible diffusion path of geoduck 6 to 12 months in advance. The prediction accuracy of the system has reached 78%, providing a valuable time window for targeted prevention and control. International cooperation in scientific research is key to understanding invasion mechanisms. The Global Elephant Clam Genome Project, involving scientists from 15 countries, has been completed. Researchers have drawn genetic maps of different invasive populations, which can accurately trace their sources and diffusion pathways. This study reveals the rapid evolution of geoduck during invasion, provided theoretical basis for the development of new prevention and control technologies. Public participation plays an increasingly important role in the global prevention and control network. The Citizen Scientist project trains diving enthusiasts and fishermen to identify and report geoduck, greatly expanded the monitoring range. In Australia, a volunteer project called Ocean Watchers contributed over 10,000 valid observation records in 2 years, helping scientists discover 3 new invasion points. Education popularization is the cornerstone of long-term prevention and control. From Nordic ocean museums to East Asian science museums, special exhibitions on biological invasion are raising public awareness. Interactive exhibition developed by Kiel Maritime Museum in Germany. Through virtual reality technology, visitors can personally experience the ecological changes brought about by the invasion of geoduck, attracting over 500,000 visitors annually, 1/3 of whom are primary and secondary school students. When the last set of monitoring data is transmitted in real time through Starlink satellite to the Global Marine Life Invasion Warning Center located in Monaco. When the member states of the Antarctic Treaty Organization just passed the agreement on biological safety in the Antarctic Ocean. We finally realized in this half-century-long game with geoduck. This seemingly crisis-like ecological challenge is actually a rite of passage that human civilization must go through to mature. The global migration history of geoduck is not just a textbook on species invasion. It is also a prism reflecting the difficulties of the human world. Reflecting the fragility of ecosystems in the process of globalization. It also reflects the dawn of technological innovation and institutional reform complementing each other. In this ecological defense war spanning 5 continents, we have witnessed 3 major leaps in governance concepts. From initial panic clearing, to mid-term systematic control, and now to intelligent symbiosis. Deep in the fjords of Norway, autonomous monitoring robots are building a digital twin of underwater ecology. In the breeding factory ship in Chile, gene editing technology makes the escaped elephant clam lose its reproductive capacity. In fishing villages in Southeast Asia, blockchain technology enables every legally caught elephant clam to have a traceable, ecological ID card. These technological innovations collectively weave a global, ocean immune network. Its subtlety lies not in elimination, but in regulation. It's not about confrontation, but about balance. Deeper changes occur in the cognitive domain. We are transcending the binary thinking of friend or foe. Learn to find dynamic equilibrium points in complex ecosystems. The breakthrough discovery by Danish marine biologist Eva Johnson's team shows that when the density of geoduck is controlled at 0.3 to 0.5 per square meter, they will not only not damage the ecology. On the contrary, it can enhance the self-purification ability of water bodies and provide shelter for juvenile fish. This concept of ecological threshold management is being promoted and applied in 23 invaded sea areas worldwide. This marks the beginning of our dialogue with nature using the language of ecosystems. Looking back at the threshold of 2035. The most precious legacy of this crisis may be the emergence of a new global ocean governance architecture. Coastal countries that used to operate independently are now sharing data and coordinating actions through the Marine Life Community Initiative. The International Organization for Marine Biosafety, established in Lisbon last year. For the first time, a unified standard has been established for the prevention and control of biological invasions in global waters. What is even more exciting is that the new generation of environmental education curriculum has included the case of pulling out a toad-like elephant in the textbooks. Cultivating planetary managers who can think across domains. Looking ahead to the ocean landscape in 2040, 3 forces are reshaping the governance paradigm. Space monitoring constellations achieve centimeter-level underwater observations, ushering in a new era of precise population control through synthetic biology. The Global Ocean Governance Convention has gained universal recognition. The Smart Oceans Initiative unanimously adopted by representatives of various countries at the Ocean Future Summit held in Singapore. This marks a shift in human understanding of the ocean from resource extraction to systematic conservation. However, technological breakthroughs and institutional innovations still require the support of values. Thai fishermen put down electric shock poles and switched to ecological fishing nets, not due to regulatory pressure. But it's because they witnessed the recovery of coral reefs with their own eyes. Japanese chefs innovate oyster dishes, not chasing fashion, but understanding the essence of sustainable use. These subtle changes, like the slow growth of underwater coral polyps, will eventually construct a new ecological ethics. When the last intelligent cargo ship equipped with the 6th-generation ballast water treatment system automatically disinfects at the port of Rotterdam. When the ecological index of the last invaded sea area returns to a safe threshold, we finally understand. The silent invasion of geoduck is essentially the ultimate test of the Earth's life system on humanity. It tests whether we can transcend national interests and safeguard the global public domain. Test whether we can restrain short-term desires and focus on long-term well-being. Test whether we can use the wings of technology to make up for past mistakes. In this exam, what we presented was not just a report on species management. It is also an epic of civilization transformation. When our grandchildren dive into clear seawater one morning in the future, what they will see is not only revived corals and schools of fish, but also a witness to the reconciliation between species and civilization. Humanity has finally learned to be a wise and restrained symbiote on the azure planet.